My name is Aida Awad. I'm the past president of NAGT, also past secretary treasurer, and very happy to be a part of this NGSS ESS working group who brings this webinar series to you. I'm joined by my co-leads on this project, Ed Robeck from AGI and Missy Holzer from Nesta. And then behind the scenes, we have Mitchell Bender-Awalt, who is working the tech magic for us back there. Thank you very much, Mitch, for joining us today. Today's webinar is entitled Passing the Sniff Test, What Matters Most When Looking at Earth and Space Science Instructional Materials. Go ahead and go to the next slide, please, Vanessa. We will, that's okay. We skipped one, but that's okay. We will have an upcoming webinar on January 14th. There should be one more in there, but that's okay. We'll have an upcoming webinar on January 14th. Title and registration information on that is being finalized at this very moment. So there it is, thank you. Very shortly, we will have the title of that webinar out to you and registration as well. So please watch for that in your inbox, probably early next week. We'll be happy to send that out to you. Also, the entire webinar archive is available on the AGI YouTube channel. There is a playlist. If you go to the American Geosciences Institute YouTube channel, click on playlists, you'll find all of our webinars there, and you can enjoy watching those over your winter break. All right, next slide, please. Please do type in not only questions, but the chat box is such a great place to have a conversation. So I know that we all wish that many of these webinars could be a little bit longer than the hour that they are allotted, and we would love to have conversations that go more deeply into certain topics. So please do use that chat box as a place to type in your ideas and your thoughts, and of course your questions as we go through the webinar. And we'll be pulling those up and keeping track of those and bringing them back at the end of the webinar today. So the presenters on today's webinar, we have Vanessa, and I think we missed, there we go. Okay, we have Jenny and Jill and Vanessa, all from West Ed, and they will be engaging us in this conversation today. As a reminder, please do type into the chat box, and at the end we will have a post-webinar survey link for you. So Vanessa, Jill, Jenny, take it away.
Awesome. Thank you so much, Ida, and thanks to the NGSS ESS working group friends for hosting us, and to all of you who are joining us today after, I'm sure, long work days, many of you already staring at your computer screens all day. So really excited to be here with you and to dig into this topic of high quality Earth and space science materials for K-12 classrooms. And we really have three goals for you today. So the first thing we want to do is just share more about our team's processes for evaluating Earth space science materials and why we think processes like these are so important. We want to get really specific next about what shifts we're looking for in materials. And finally, we want to leave you with some resources to help you decide which design features are important when you yourself are either designing or evaluating Earth and space science materials. And so just a quick overview of our agenda for today. We're going to dive right in, first of all, with some introductions. And so I would love to hear a bit more about who's joining us in the crowd today. And so if you can just type into the chat box, let us know your name, what grade levels you work with, what state you're from. That's always very interesting to us. And the last point there, we'd love to hear just one, what you think is a unique challenge or opportunity for teaching Earth and space science with today's science standards. So I'll give you a moment to gather your response here. I'm excited to see off the bat, we have some K-5 teachers as well as folks who work with pre-service. Great. And don't forget your unique challenge or opportunity for teaching Earth and space science with today's science standards. As you all are introducing yourselves in the chat box, I'm going to take a moment to do a few introductions of our webinar presenters. I'm Jenny Sarna formerly from Achieve Science team, and now part of the NextGenScience project at Wested, which we founded in April. And I'm joined today by my colleague, Vanessa Walbrink, Associate Director of our project, and thrilled to be co-presenting today with our colleague, Jill Grace, who directs Wested's K-12 Alliance project. And both of our projects focus on working with educators and leaders at all levels of the system, from the state education office to the classrooms. And it's about teaching science in ways that make a difference for kids. And we do this in a number of ways, from NextGenScience's tools for evaluating units and lessons, like the Equip rubric, and posting high quality examples on nextgenscience.org, as well as providing some of the learning and tools that are really specific for moving classroom practice, such as some of the work the K-12 Alliance has done through the NGSS Early Implementers project. And both of our projects, though, think a lot about instructional materials, because we know they inform both what and how educators can engage students with science. And we know they have a huge impact on what students experience as well as what students learn. So we're going to really kind of think about those things today, and especially in light of some of these challenges I'm seeing popping up in the chat box. So you all have sort of read our minds. I'm reading here. We think earth-based science in the NGSS and today's science standards offer a real opportunity for really rich, engaging environmental phenomena, especially the opportunity to authentically model cross-disciplinary integration. Many of the earth-space science phenomena we see in the world require multiple disciplines to explain. We're really excited about that. But we also have heard sort of the difficulty of making some of the space science phenomena relevant. We know that, especially in K-12, some of the structures in high school don't afford sort of adequate time to teaching of earth and space science. And I'm seeing here this idea also of the rigor of those courses if they are offered. I think as a root cause of that, the quality of materials and also the content knowledge, the credentialing of teachers, just having sort of opportunities for educators to learn that content and to understand it deeply. It's sort of all connected. And so we want to think about materials as sort of a tool and a solution in this space. And really excited to dig into this topic with you today. We know the research says, why materials? We know the research says that they make a difference, and especially when coupled with professional learning. We also, though, know that not every design of a way to teach a topic is going to be as effective. So that we want to think about what are the designs of learning experiences that are going to advance student learning the most. And we both of our projects know, like, this is critical for equity. And so we've seen the research on the impact of well-designed learning experiences for moving student learning, particularly for students in disadvantaged schools and from underrepresented populations. So that's really the heart of our work, is saying, how do we make sure all kids get these experiences? And so if we know that not all materials are created equal, and it's a big investment and can have a huge impact on learning, how are we going to pick the best ones? And we want to think about that today. And I'm going to actually turn it over to Vanessa to dig a little deeper here.
Okay, thanks, Jenny. Hi, everyone. As Jenny said, this work is really important and makes a really big difference for kids. We can't just take the claims that publishers or developers are making about their materials being high quality or designed for the NGSS at face value. We have to dig in for ourselves, or maybe have an independent third party dig in to see if resources are truly quality. So what we're going to do now is we're going to show you broad outlines of 2 different lessons that are targeting similar Earth and space science content, and we're going to do a little evaluation together. And so for each lesson, I'm going to ask you to think about these questions. And so get your chat box ready, because as we kind of go through the lesson outline, I want you to answer in the chat any of your thoughts to any of these questions. What's motivating the learning? Who is the knower or doer of science? How do students develop important science ideas in the lesson? And what opportunities do students have to share their ideas? So to dive into lesson A, I'm going to read this outline out loud as you're thinking about these questions. And so as I'm reading, go ahead and put your answers in the chat. So lesson A, a teacher shows a demonstration in front of the class showing ice cubes melting in salt and fresh water. Students predict which cube will melt faster and draw and label the experimental setup. Students make observations and a couple share them with the class. The teacher then charts the class results and tells the class this has to do with density, describes it a little bit. Then students create explanation statements in groups and present to the class. And then at the end, students are given readings with an explanation of ocean currents, climate, and melting ice sheets. So go ahead and in the chat, just anything that strikes you about this lesson. Okay, somebody mentioned that the demonstration at the beginning of the class can be motivating the learning. Students share their ideas with the class. A couple, great. It's largely teacher-centered, and the teacher appears to be the knower and the doer of this class. The motivation is because this is what we're doing in class today. Okay. Students are given the heart of explanations and not generating it themselves. The knower is the teacher when she tells them that it's related to density. I love how in a lot of these answers, you're all providing evidence for your answer as well. That's really nice. Students see, observe, and measure at the beginning, and their curiosity is piqued with the demonstration. Again, seeing this comment again, that the teacher is doing a lot of the heavy lifting here. Another great point Charlotte made, that some students may have an opportunity to share, but not all, because it's with a full class conversation. Okay, thank you all so much for sharing your thoughts. We're now going to look at lesson B. A little bit more text on this one. So same thing, I'm going to read through the lesson, and as I do, go ahead and put your thoughts into the chat box. So with lesson B, the teacher shows a glacier image in Arctic ice melt animation. The students share their prior knowledge, make observations, and ask questions about the animation and implications for the Earth. A student question about what affects ice melting speed leads to a conversation about salt versus fresh water. They make predictions and conduct an experiment. The class discusses systems, and students develop system models to explain what they saw happening with the ice. They share models with each other, discuss their ideas, receive feedback, and read about the effect of temperature and density. They revise their individual models. At the end then, they argue from evidence with each other and create a group consensus model. They discuss how this helps explain the Arctic ice melt animation and real-world implications for the Earth. So, curious to hear. One comment, this is a much more student-centered lesson designed for student voices to be heard. And maybe one reason for that is the classes are, or the students might be working in groups instead of just full group conversation. Small groups, I mean. Multiple opportunities for students to share their thoughts and ideas. Motivation is the students' questions. Students are doing the science based on questions generated from the phenomenon. Multiple revisions of a model. Emphasis is on revision, not just being given information, but how that information changes your thinking. That's a great point. Kids are arguing from evidence. The lesson replicates how researchers and scientists actually work, lots of collaboration and revision. Students are exploring and generating ideas using science and engineering practices. Sounds like we have a lot of NGSS expertise in the audience today. And students share their models multiple times with each other. So again, that idea that student ideas are at the forefront and being shared in multiple ways. Thank you. These comments, these are, you've had some amazing feedback. Thank you guys so much. I want to actually now take a look at lesson B through a different lens. And that's just these 6 components here of that are related to the NGSS. As I mentioned, it sounds like you all have a lot of NGSS expertise in the audience today, and a lot of these already came up. And so I'm curious, what are 1 to 2 connections you see? Several of you already actually made these in your chat comments, but what are some of the connections you see to NGSS design as you're looking at these components here between the lesson and these? Go ahead and put some thoughts into your chat. Okay, I see students engage in the science and engineering practices and cross-cutting concepts, which is the second component here. They're talking about systems, they're engaging in argumentation with evidence. They're modeling, students are showing their ideas via models. Somebody mentioned earlier the student ideas portion, they have multiple ways to share ideas here. Relevance and authenticity, because they're looking at a real glacier image and animation. So there's some argument to be made that this one's a little bit more relevant and authentic than the lesson A. Building on students' prior knowledge, this component here, somebody mentioned that when the phenomenon is introduced, students share their prior knowledge. Okay, great. You guys are amazing. You've made all of these connections. And so these 6 components that I just shared are actually the criteria of one of our evaluation tools called the NGSS Lesson Screener. And that tool is just a quick one with just 6 criteria to determine if materials are on the right track and worth digging into with a more robust tool like our Equip rubric for science. And one thing I do want to say here is that all of these criteria are designed to create more equitable science instruction. You might not see equity explicitly listed as a criterion, but they represent, you know, these criteria are not just nice to have, but they represent our most up-to-date research about how to engage all students in science. So for example, instead of engaging in knowledge and practice to solve a problem or explain a phenomenon, students have traditionally, maybe decades ago, have just learned about a science topic. And that way of teaching science ideas in general, like we're going to learn about unbalanced forces today, might work for some students, but often leads to decontextualized knowledge that students are unable to connect with their prior learning or even apply when relevant in a real world situation. It reminds me of those stories of kids who have the equation for photosynthesis memorized, but can't tell you where the mass of a tree comes from. So it's kind of separate as taught as a science topic. And so anchoring the development of science ideas in investigations of phenomena with these features helps build a more usable and generative knowledge that can reflect how we learn best and in particular help reach all students. So I just wanted to emphasize this equity component since it's not explicitly listed as a criterion here. And so I mentioned that those criteria are from one tool, our lesson screener, but I want to share a little bit more about how you can use tools and processes to start thinking about NGSS design, because there are a few options depending on what you need and what you're doing to make sure your materials are high quality. And so, before I go to that, whatever tool I'm talking about in this section, you might notice that I'm using the phrase designed for the NGSS rather than aligned to the NGSS. And I just wanted to point that out because it's not as simple as making sure ideas and practices are covered in a lesson or a unit, but that materials are really structurally designed from the ground up in a way that reflects the innovations we just talked about. So for example, is the phenomenon or problem driving the learning, or is there maybe a phenomenon present, but it's just being used as a hook before students learn about science topics in a more traditional way? They're very different designs. So it really, using the word designed instead of aligned to kind of is just our way to drive that point home a little bit. And so, as I mentioned, there are evaluation tools for different things, different kind of grain sizes here that you want to evaluate. We've got NextGen Time, which is for full program evaluation and implementation, Equip for a unit. The lesson screener, which you just saw the criteria from, is a shorter version of Equip that could be used for a lesson or unit. And then the task screener is for looking at the quality of an assessment task. And so for every one of these tools, there are some best practices for use here. And I want to first emphasize that these tools are most powerful when used in a group of people. The conversations you have to push each other's thinking really, truly deepens your understanding of NGSS design. So using these tools are not just to get the end product of having an evaluation, but it really is a learning experience for everybody involved. And it also makes sure that you have a common understanding of these criteria and what features you're looking for as a team. So the first part of the process we always recommend is calibrating understanding of criteria, which is no easy task. But this might involve looking at a common example lesson first and making sure you all have the same interpretation, maybe doing some shared learning together. And then you separately, individually, review the item you want to evaluate and collect evidence to justify your ratings in the tool, just as you guys were sharing your evidence when you were making comments about lesson A and B earlier. So having kind of those, the real evidence of what's in the materials to back up your claims that this is phenomena driven, that this has the grade appropriate science and engineering practices. It can take a while to pull all of that evidence. And then this is where the magic happens, the meaningful consensus conversations. You bring your evidence and your ratings to that conversation and come to consensus for each of them. And that can be, that's definitely a learning and a growing process for everybody, but it is so meaningful and leads to a lot of learning. And with that, you're able to make your final determination. And so I wanted to pause here, just show you a little guide that shows kind of what tools or what resource you might use for different scenarios. And in the chat box, I'm curious, which of these tools have you used before, or which ones do you think would be most useful for your context? We have, you know, evaluating, selecting, piloting, implementing a full science program. We have spot checking units to make sure your current curriculum is high quality. That might be with Equip or Lesson Screener. Maybe you want to select a unit for a unit study or unit replacement so your teachers can see the NGSS shifts in action. Or maybe selecting, modifying, or developing classroom tasks to monitor student learning. And that's a whole challenge of, trying to elicit whether students can make sense of phenomena using the 3 dimensions. And for that, you can use the science task screener as support. So I see some have used NextGen Time or would like to, looking to adopt a high school NGSS curriculum for a district. Yep, perfect use. Great to see that some of you are using the Equip rubric and the task screener all the time. That's awesome. Very cool. Used all of these tools at some point over the last few years. And so one thing I want to point out, we haven't really talked about the science peer review panel, which is listed here. This is a collection of expert teachers across the country who evaluate free and publicly available units with the Equip rubric free of charge, now limited to middle school units. But they share online the highest quality examples so that people can use them as concrete examples to learn from, even though the examples posted don't form a coherent curriculum that you could fully adopt. But these units can be really valuable for professional learning purposes and to really see concretely what this could look like in a classroom. And so one of those high quality examples posted called Understanding White Sharks has earned the NGSS Design Badge, which indicates the highest rating on the Equip rubric for science. And I think, out of well over 300 units the PRP has reviewed, only 14 have earned that rating. So, and always with a lot of hard work involved. And so next, one of the lead developers of that work, Jill Grace, is now going to share a bit about the experience, the process, and some of the key features of that unit. So I'm going to pass it over to Jill.
Thanks, Vanessa. Hi, everybody. So excited to be here today. And yeah, I think you'll probably have a takeaway of this was a lot of hard work to actually develop this. And this was a labor of love for about 3 years. I like to think we had some influence in helping develop Equip over time because the review process looked very different initially than it ended up at the end. But if you go ahead and click for me, Vanessa, you can see that this is a series of 10 lessons that focused on students explaining a possible increase in white shark encounters and concerns of the public. And we highlighted Southern California predominantly in the sequence. And we'll go through the development process in a bit. But for now, I'd like to highlight that this was a project of our early implementation initiative in partnership with the Shark Lab at Cal State Long Beach. And our priority was to create an integrated design for NGSS learning sequence for 8th grade. And that need came about just from a lot of communication from the field that was really needed from the field. So we can go ahead and advance to the next slide, which you can't read, so don't worry, later you can dig into the materials and look at that more closely. But this was our conceptual flow for the unit, and it basically was informed by 3 rounds of feedback from the science peer review panel. And they helped inform the overall sequence development that you see represented in this conceptual flow. To explain the anchor phenomena, students really begin in the sequence by starting to ask questions that lead them to wonder how we can establish that white shark encounters are actually increasing and think about population size over time and time being represented by more ancient and recent. And in that whole first chunk that you see there, students really establish that they think of fossils and then human records that we call Fisher's log to realize that they can't get the information they need about white sharks and establishing, baseline for the population. So that leads them to question how scientists today are studying that, moving us into the second chunk. which is where students seek to build understanding of that by studying populations using tracking devices. And that brings in a lot of physics concepts like non-contact forces and waves. And from that, students move into the last chunk where their ideas work in service of really what I think is the heart of the sequence, which is an Earth and space science standard around human impact. That informs a public service announcement students design to help educate a target audience on what we know and understand about white sharks and human activity and our impacts on the shark population. So if I step out for just a second, at first glance, when you look at instructional materials, if you find something like a conceptual flow like this or a storyline like this, it might actually indicate that work actually went into building coherence in the learning. If you see clearly defined phenomena, not topics or concepts, and you can see the integrated three-dimensionality being pointed out, those are good signs. So you still need to sniff it out further, but it does show some promise in the materials. So moving into then the process that we went through, I'll step back in and consider the behind the scenes part that went into developing it. And I have to give a nod to some history here. This all started with the early implementation initiative South team that was charged with planning a year of instruction to be presented over 3 different summer institutes for 8th grade teachers in our initiative. And in that first year, I was partnered with Ed Price, a physicist from CSU San Marcos, and Lisa Martin Hansen, science education from Cal State Long Beach, to do that work. And if you look closely, you can actually see us starting in a hotel ballroom, which we are weirdly feeling nostalgic about right now, and cutting up standards so we had pieces to move around and help shape our thinking. And we knew we wanted to start with waves because we knew that was a high need for 8th grade teachers who had never had to teach that before. Ed at one point suggested we focus on bird tracking, to which I replied that I had a marine biology background, so I'd be far more useful if we did something marine, and we eventually agreed to focus on sharks. Sharks have dinosaur factor for kids, so we thought that would be pretty exciting. So fast forward to 2016, we, in collaboration with Achieve, recognized that there was a high need for 8th grade teachers to have an example of a high quality integrated NGSS unit. And so we partnered with them to start that work. It started with a team of 5 teachers that formed the first writing team. I will comment, we started the work on a Saturday in September while a bunch of colleagues were on vacation in Italy. So we decided to make it a brunch meeting. And the work proceeded to write the lessons in the sequence. It was sent to readers and field test teachers that gave us feedback, and eventually to the peer review panel. And interestingly, it was evident that what we really produced and started with looked a lot like the lesson A that Vanessa shared with you all today. We needed to really kind of take a step back and think about how we made some important shifts to really attend to student thinking, which were pretty much absent. So we built charts to process all of it, and knowing my audience, I want to draw out for you our fossil lesson, where you, looking at the feedback that we got, so if Vanessa clicks for a moment, I think our chart will pop up. And on that chart, we had a note, how do we change so students drive the investigation? Because we were working with a lesson that was a well-known framework for how to teach something like geologic time and fossils, but it wasn't really driven by how students thought about it. So if we advance the slide again, enter Tony Metcalf from CSU San Bernardino, who helped us turn that fossil lesson on its head. And students eventually come to realize that not all fossils are useful, shocker. And you can see here, we were in a different hotel ballroom where Tony scratched out a probability activity that became central to the lesson. So at that point, the writing team also shifted down to 3 writers. So myself stayed on, and I brought on board Katie Beck, who had taught middle school before, but was a high school physics and AP physics teacher, and an early implementer teacher, Chris Olivas from High Tech Middle, who had expertise in project-based learning. And we edited the sequence and went through a second review And once again, process the info on charts that this time took over my house, and to really kind of try to get into the heads of kids. So I had to share the last picture because this is the Sniff test presentation. This is my puppy house guest, Murphy, my friend's dog, who is clearly annoyed at all the work and lack of attention on her. So moving forward, we went through another round of edits. We can go ahead and click this slide. And, you know, throughout, we ended up getting input from about 300 8th grade students and their teachers. We had our final peer review panel review and finally earned the coveted NGSS design badge. But I think it's a moment to pause and just recognize that it was a huge collaborative effort to get to that particular stage. If we click one more time, what I'm going to do is go a little bit into some of the feedback from the peer review process, and I'll highlight 3 criteria and some of the specific feedback from the peer review panel to help you kind of get a sense of how the materials really shifted through that process. So if we click one more time, one of the things to highlight was really the use of phenomena in the sequence, and input from the review helped us home in on putting student ideas and thinking at the forefront to help them explain what we do understand about the white shark population, and more importantly, our relationship as humans with them and how we can alleviate public misunderstandings and concerns. And we really kicked off the sequence with a press release from the Shark Lab that was designed to really just get the kids to talk and leverage their prior knowledge, including their fears. I'll note for just a moment, because you'll see this on the student artifact in a second, that we originally had used an article from a local newspaper, but we had to switch it because the paper wouldn't allow us to share this through Creative Commons. So advancing the slide, you can see the student artifact here where they were kind of processing their thinking from originally the article, which became the press release. And the peer review panel noted that the 3 dimensions really were working to support and surface and drive student thinking, as you can see from the artifact. And importantly, it also just served a secondary purpose to really get some of the kids' fears out. Like, are they dangerous, right? Should I be worried about them? Why aren't people scared, right? So digging into the unit then, we kind of move into relevance and authenticity. And an example of this would be the Fisher's Logs lesson, where we really drew out that human impact standard, and students worked through a reading that really highlighted the plight of a fisher and included some historical context as well as data from the Shark Lab, including this figure that you see here, where we're showcasing basically 100 years of landings of white sharks off the coast of California. And students work in sort of a literature circle style to focus on that in expert groups, and they take on 1 of 4 perspectives to focus their analysis. So one of those is the cause and effect analyst. So if we click one more time, you'll see that description where they really dig in and look for those relationships and can they explain those relationships. And if we click one more time, you'll see a student artifact from that. Over and over again in the artifacts, we saw that students were really struck by the influence that a movie has, and that we can actually see that in the data. So if you look at following 1974, at the release of Jaws, we see a slight uptick in the landings of white sharks. And remember, this is California, not the East Coast, where the movie was centered. But that like floored the kids. They couldn't believe that that actually could happen. So that was really powerful for them and really relevant for them. So towards the end of the sequence, really feedback on student ideas was also positive. And an example of this is where we eventually go with the idea of sharks and humans and the relationship that we have with them. And students are able to pull together what they understand about how scientists study sharks with tracking devices and what the data reveals. And again, students were really struck to finally like pull this picture together and realize that the coastal waters off Southern California are nursery ground for white sharks. And they spent a lot of time grappling to make sense of Shark Lab data, as you can see in this figure here. So they finally end the sequence with a public service announcement. So if we click one more time, This is a slide from one student's public service announcement that they created. And you can see that it really touches on their understanding of that relationship between sharks and humans. They decided to circle back to Fisher's logs data, something that was important for them to make that connection. You can see they decided to color code, and they're highlighting that more young of year and juveniles were off the coast. If I focus back on 1994, which the students call out, you'll see that there's a decline in the landings of white sharks off California. And that was actually because of two key pieces of legislation that were passed in California in 1994. The first that banned nearshore gillnet fishing, and the second that prohibited the catch and landing of white sharks. And all of that was intended to alleviate the impact of the increase in the human population and our demand on fishery resources, but it had this wonderful side effect of protecting the babies off the coast. And so students realize that there's an increase in white sharks today because the sharks that we're seeing today are actually the babies protected by that 1994 legislation that grew up and finally started reproducing. You may or may not know that female white sharks can take up to 33 years to become reproductively mature. So thanks to all the teachers and the peer review panel members that really helped shape and designed this design for sequence that really gives students the opportunity to work with really modern, relevant, and interesting science. So that was the design. So I'm going to kick it back to Vanessa.
Thanks so much, Jill, for sharing that unit. I feel as you were talking, it's really clear sort of both the passion of all the folks who worked on that and really the intentionality of how we put students in the driver's seat and get them to really sort of do the work of scientists and get them wondering. I love the product, the PSA as sort of the final student.
Single marker and scissors that are
as the final student artifact. It's really really powerful of sort of what students latched onto most and we're really passionate about. So we are starting to get some questions in the chat box. So I think we will at this point kind of wrap up here our presentation. And Chris, your question, Christopher, is there a way to get a closer look at the unit? Absolutely, it's on our next slide. We just wanted to wrap up with some quotes from students here of just how their experiences were using this unit, because we think it's a really good reminder of the power of these learning experiences and what they mean for kids. And so these are, you can see that the Understanding White Sharks unit, there's a bit.ly there for that unit. Vanessa just put that in the chat box. And with that, I know we've been talking a lot about sort of the earth science piece, but I want to end with a quote from one of my favorite space scientists that I think really is a nod to the power of this type of learning and how important it is for kids, and really about students are capable of some of the most phenomenal things and deepest thinking if we give them those opportunities. So thanks to Mae Jemison for that. And with that, a big thank you once again to our NGSS ESS working group for having us here. And I will open the chat box up for questions, or if you are would like to unmute your mic and ask a question, feel free to.
Thanks very much for a great presentation, ladies. Really appreciate it. One of the questions that came up as we were going through the slides is thinking about the situation that some of us are finding ourselves in, whether we're teaching face-to-face now or hybrid or fully remote, and who knows where we're headed in the next few weeks or so. But how might the tools, maybe particularly the lesson screener, be modified to really help us understand best practices for those different kinds of ways of engaging with students? What do you think about that one?
Vanessa,
Oh.
that's going to go right to you.
Yeah, absolutely. I can actually share. I promise we didn't even set this up, but we have a resource called Keep Teaching Science that focuses on exactly that. It's looking through the lens of all of the lesson screener criteria here. And what we did is we partnered with really thoughtful and hardworking developers with units like the one Jill shared with us. And we knew they were all doing work to adapt their materials for remote learning. And so this resource here, Keep Teaching Science, and I'll put this link in the chat, shares through the lens of each of the lesson screener criteria, the adaptations they made to remote learning that maintains that criteria. So how do you make sure your lesson remains phenomena driven even in remote learning? How do you ensure the 3 dimensions are still being engaged in, developed, used, even in remote learning? So these are specific strategies and concrete examples that you can actually look through for each of the criteria. So strongly encourage you to check that out because there are a lot of people who've already done the work to come up with a lot of these strategies. So, oh, thanks, Jill. Jill already posted the link.
Great. Yeah, thanks. Missy, I think you were watching the chat box too. Did you have any questions that popped up in the chat box before I ask another one? Missy, you might be muted.
Thinking about entry points, and we have teachers that are at different points of their integration of NGSS into their curriculum, into their classroom, and building that confidence level. Is there? I know that the lesson screener is a terrific place to start, but can you give some hints to a teacher if just to kind of getting their feet wet and converting what they're doing and everyday practice into best practices related to NGSS?
Yeah, I think, not to be redundant, but I think looking at some of the high quality examples like the shark unit that are posted on our website. I mean, nothing beats a concrete example to see what these shifts actually look like. You can talk about phenomena, you can talk about the 3 dimensions and unpacking the standards, but until you actually see a real example in a classroom, it's really hard to kind of picture what it looks like. So, I could point to, we have a resource that describes a little bit more about what phenomena driven means, but I think really this page of high quality examples that have been reviewed by the peer review panel is a great place to start. And to do, if you have the opportunity to do a unit pilot or unit replacement as part of a unit study with other teachers, having those conversations, pushing each other's thinking, talking about what worked, what didn't, is one of the best ways to get your feet wet, I think.
Terrific, thank you.
I can build on that too, that really that was the point of the early implementation initiative. And we did not have materials that were out when we started that work. So with many of our teachers, and that was a K-8 project, it really started with, can we just start by embedding phenomena into the work that we're doing and start with that? And that tended to be a comfortable starting place for teachers. Sometimes it's also just, let's start incorporating a couple key practices like developing and using models. I found when we started to stretch our work into high school that it often was a lot more productive to start with just flipping your lesson. So rather than doing a lab as confirmation, can we start with something like that first and use that to generate questions and wonderings from students to then necessitate the learning that's about to happen. So that structural shift at high school was a lot harder for them. And so can we just flip the lesson and see how that feels and what happens with student thinking as a result. So those tend to be a good starting place, I think, for anybody, if you're not going to, do a replacement unit and try something that's completely new.
There was a question in the chat box about any earth science examples that have passed the screening. And so if you go to the quality examples page, you can actually sort by science domain. And so if you sort by earth and space science, you'll see there are a handful of examples that are examples for earth and space science. And then I would also encourage you to choose that integrated domain. If you select integrated, you'll see a few more pop up there as well. So, but I'm gonna put this out as my call to action to this group, to especially the peer review panel is always looking for more middle school materials to review and provide feedback on. And we definitely have a shortage of those high quality examples in the field. So we're looking at you all to submit some more examples for us to review. We would really love that.
I see another question in the chat. What if you teach part-time and you meet with your class only once a week for 10 weeks? That is a very challenging situation, and I think an increasingly common situation now with remote learning. People are facing reduced instructional time for science. And some of the current thinking is to really prioritize giving students a chance to make sense of phenomena and problems. I think when you have such little time, it's really tempting to just, cover some content or kind of go back to some of the more traditional ways of learning science, maybe just focused on the disciplinary core ideas. But we would really encourage people with limited time to find a way to maybe use some high quality instructional material examples and modify them, prioritizing the student sense making and reasoning and kind of student-led engagement in those in knowledge and practice together. Which I know is not a straightforward answer and it's not an easy answer, but that's what I would recommend as just a first priority there.
We have a couple of questions in the chat that are asking similar things, and they're related to high school and schools that are integrating earth and space science into 3 courses. Maybe they're called biology, chemistry, and physics. Maybe they're called something else, and trying to find materials that work in those situations. And they're wondering what your thoughts are and what your suggestions might be related to that question / problem.
Well, we don't provide curriculum recommendations for full programs. I think, again, sorry to kind of repeat myself, but I think when you're looking for a coherent full program that integrates the topics as you want, that just needs to be one of your criteria when you're in the evaluation process, and really having a robust process next gen time where you have a team of people, you have your priorities for curriculum, like you need earth and space to be integrated with X, Y, and Z, or you need, this specific situation to do a full evaluation with these NGSS criteria in mind, and just putting it out there to publishers, developers, anyone who creates materials, that this is what you need and this is what you're looking for. And then choosing the best you can and modifying when what you get isn't perfect, because it never will be perfect.
And I can echo that just we acknowledge this is a problem for high school. So, or I can acknowledge that this is a problem for high school. And there's a lot of people struggling with that very same question that you are. You're not alone. So, I can anecdotally say there's some districts that have been working on it and have had teachers try to do some work to revamp. I don't think any of that's publicly available. But we can say it's enough of a problem that if you're familiar, for example, with Open Syed, they're actually going to high school development next because they recognize that this is a concern of the field. So just, put out that sniff test when you do find materials, as Vanessa's suggesting, just to, think about where are they? And more importantly, when you go through the process like that, you recognize where the strengths and limitations of those materials are. And where you know that, you know where you can build on. So it's definitely worth, using the tools to help you be able to determine that.
Thanks very much. So we had one last question that we don't really have time for, but I want to ask it anyway, because I think it's important to this particular audience that we have gathered here today, and that is that we've got these great tools and they help us evaluate after the materials have been developed. What materials are there out there that really help support people in the development process, guide them through that, because that can be a little bit scary and obviously very time consuming, as Jill told us. What do you think about that one?
That is a great question. I would start with, I think these tools we know actually a lot of developers who are using these tools to also help them think about the development process in terms of just establishing their priorities when they're creating their sort of design blueprints. I think the power of concrete examples, again, I would go back to the, looking at sort of badged units and seeing their approaches can also help one think about what is sort of the blueprint, as well as in the instructional frameworks maybe that might be useful here. Thanks, Julie, for putting in the chat 5 tools and processes. I think as far as a tool specifically designed from start to finish to think about sort of unpacking and setting priorities for standards and phenomena, that is also a free and publicly available resource there. Yeah, and the other thing I would just add is just like the importance of working as a team to do this design work. I think, Jill, your story really demonstrated that this is, there's power in numbers here and sort of getting like-minded people together to do this design work.
And I also shared in the chat, 5 tools is wonderful. We also ended up developing some tools in the early implementation initiative that helped our teachers do that work. So I just shared that evaluation report link as well.
Thanks very much. Thank you very much for your presentation today. If you could bring up, great, thank you so much. The post-webinar survey, if you want a certificate of webinar participation, this is the only way to get it, but we really do value the feedback from everyone. I dropped the link to the post-webinar survey into the chat box. Please do click on that so that we have feedback from you on this webinar. And then our next slide, the webinar series is brought to you by the NGSS Working Group, which is a collaboration between 3 organizations. The first being NAGT, who has a full webinar series. Don't know why that's not showing up very well. I will drop the link into the chat box for information and to sign up for information on that webinar series. And next slide, please. Missy, if you want to talk about Nesta quickly.
Yes, feel free to come to the NESTA website, and we're a member organization and members, an organization for Earth and Space Science educators. Come join us.
And Ed, on the next slide for AGI, please.
Thanks all. Thanks for being here very much. And thanks for all you do in Earth and Space Science education. AGI is a federation of member societies. And education is just one of the things we do. Please visit our website. We facilitate a lot of different programs, including Earth Science Week. We'd love to have you join us in those different opportunities.
Thanks very much. And just want to thank you all for joining us today for this webinar. Please do complete the post-webinar survey. We very much appreciate your feedback, thoughts, and suggestions and ideas there. And if you want to contact any of the 3 of us, Ed, Missy, or myself, our emails are up on the screen. Thanks very much for joining us this afternoon. Have a great rest of your day. Stay safe and stay well. And maybe stay warm too.
Thanks, Ida. Have a great one. Take care.
Thanks, everybody.